Good morning, students. Am I audible? Okay, ask everyone to join. जल्दी जल्दी सबको इन्फॉर्म कर दो हाँ जल्दी. Okay, so let's start. So good morning, all of you. This is a class of Railway Engineering Professional Elective 1. Okay, so do you remember what we have discussed in the last class? You can write in chat box or you can also speak up. What we have discussed? Anyone? याद है कि नहीं? लास्ट क्लास हम लोग ने क्या पढ़ा? Gradients. Good. So yes, we were discussing about gradient in railway track. Fine. So let's go back to that class. Previous class. We'll go for a little bit revision. Then we'll go to the proceed. Okay. And we have not finished yet about gradient. So in this class, we're going to finish about the gradient. Fine. So basically, what is gradient? Gradient it's a kind of, you can say, the property, or you can say a part of geometric design of railway engineering, as well as for highway engineering also. Okay, so basically gradient is defined as a slope which can be connecting lower point to higher point. Okay, so there are different types of gradient we have discussed in previous class. Do you remember how many types of gradients are there, or types of gradient that can be provided in railway track? How many? Just write down the number, or you can also write the name if you remember. How many types of gradient we have discussed? Anyone? कितना टाइप का ग्रेडियंट्स है इन रेलवे ट्रैक? याद है कि नहीं? Okay, so basically, anyone want to respond? So anyway, so in general, there are 4 types of gradient, if you remember. Clear? What are they? Gradient, provided in the station yard, or you can say the minimum gradient. Then second one is your what? Ruling gradient. Third one is your momentum gradient, and the fourth one pusher gradient. Okay, so in the last class we have discussed about uh, minimum gradient, that is the gradient provided in the station yard, and the ruling gradient. Okay, so in today class we're going to discuss about your momentum gradient and pusher gradient, and also we're going to discuss about grade compensation in curve. Fine. So let's go for revision again. Let's go back to the previous class. So what is your minimum gradient? That particular gradient which is provided in the station yard. Okay, and it is main purpose of providing a gradient in station yard is to drain out the water, basically. Okay, it's a very small amount of gradient that is provided in the station yard, and main purpose of the particular gradient is to drain out the water from the station yard so that water will not be stuck in the yards. Okay, so next one is your uh, ruling gradient. So ruling gradient is higher than station gradient, or you can say minimum gradient. Clear? So what is the basic definition of ruling gradient? So ruling gradient is that gradient provided in the railway track over which a train can move with the same engine power, or it does not need external force. That means a particular train can move smoothly over a ruling gradient with the same engine power and without providing any external force. Okay, so that is your ruling gradient, and ruling gradient is higher than minimum gradient or the gradient provided in the station yard. Okay, so how we have discussed, how we have explained these things. So first let me share my screen again for you. So my screen is visible, right? Do respond. Okay, okay, so how we have this explained. Okay, so how we have this explained that particular thing. Wait a second. Okay, just okay. So generally, how we have explained that ruling gradient. So suppose this is your horizontal ground, natural ground, okay, and suppose This is a particular gradient, okay, just a slope. Suppose a train can move smoothly over this slope, fine. Suppose this is your theta 1, you can consider theta 1. Next, suppose we have raised this particular slope, suppose this is your theta 2. Suppose particular train can also move along this slope with the same engine power, okay. Now if I again increase this slope up to this level, suppose theta 3, okay. So assume that the particular train, the same train, is not able to move along this slope, okay. So from that point of view, we can say a train can move up to this level, the second one, up to this level, up to this slope, can move above this slope with the same engine power. So what is the this particular slope actually will be given denoted as a ruling gradient, okay. So okay, so like this we have discussed about that, about ruling gradient, okay. So ruling gradient is higher than your minimum gradient, fine. So after discussing about ruling gradient, let's discuss about that one, momentum gradient, fine. So what is momentum gradient? First of all, before going in the detail, let me first explain to you what is actually the momentum gradient, okay. Okay, so now suppose I'll again draw this a hill. Suppose this is a hill, okay. Now suppose again I'm showing you, suppose imagine, just imagine this is a horizontal natural ground surface, okay. This is your, suppose your minimum gradient, so G minimum gradient provided in the station yard, okay. And this is your ruling gradient, suppose this amount is your ruling gradient, okay. So I told you that ruling gradient is higher than minimum gradient, okay. So this amount of slope is provided in the station yard, and this is the ruling gradient. What is the significance of ruling gradient? That means above this level, train can, above this slope or above this ruling gradient, a train can move smoothly with the same engine power, with the same engine power, okay. Now from this point of view, we can say any higher slope, any slope higher than ruling gradient over a particular slope which is higher than ruling gradient over the particular slope, a train cannot move with the same engine power, correct. But but there is a possibility, there is a possibility, or we can make the train can move over a slope more than the ruling gradient. We can make a particular train to move over a slope which is more than ruling gradient with the same engine power, and it is possible only if there is a combination of a higher gradient as well as okay, as well as a downward gradient. That means what is momentum gradient? Whereas there is a combination of downward and upward gradient, the momentum gradient will be used. Got it? That means suppose the train is coming through this downward gradient. Suppose this is a downward gradient. I'll draw a train. Suppose this is a train moving along this downward gradient. Okay, now when it comes down to the downward slope, it gains some energy, momentum energy. Okay, and this train use this momentum energy to move upward up to certain level. Okay, and from that particular point, a train can move smoothly over this gradient. That means this particular train use the momentum generated during the downward movement, and that particular train use this momentum in moving upward direction in the upward gradient, which is actually more than your ruling gradient. Okay, so this is your downward gradient and this is your upward gradient, but this gradient you can see it is higher than ruling gradient. Okay, and this particular gradient is known as your momentum gradient. This is your momentum gradient. Okay, so momentum gradient is higher than ruling gradient and ruling gradient is higher than minimum gradient. Okay, so you can also write mo, also gmo for momentum, because it is also m, right? So in different book, different notation may be there, so don't confuse, try to understand the concept first. Okay, so again repeating the definition of momentum gradient. So whereas there is a combination of downward and upward gradient, when there is a combination of downward and upward gradient, the momentum gradient will be used. This is a momentum gradient. Okay, and it is possible to operate on this gradient. Okay, it is possible to operate, or it is possible to move the train over this gradient, which is higher than ruling gradient, with the same engine power if there exists a combination of downward and upward gradient. Okay, so in some competitive exam, a question may arise when the momentum gradient will applicable. When there is a combination of a downward and upward gradient, then only the momentum gradient will be applicable. Okay, why it's called momentum gradient? Because the particular train used the momentum energy to move upward. Is it clear? Clear, right? So after this, next we have the fourth one, pusher gradient. Okay, or helper gradient. Sometimes it is also known as helper gradient. Fine. So from the name itself, it is understandable that you need something external force which push the train in upward direction. Okay, so basically I again draw the drawing. Suppose there is a downward elevation, then again upward elevation, like that. Suppose this kind of a gradient is provided here. A train have to move from this point and have to move like this. Okay, suppose this is a train. Suppose this is a train need to move in this direction. Okay, so this train need to move along this direction. Fine. Now from the design, okay, from design analysis is found that the particular train, even with the momentum energy, it moves only up to this point. Okay, only can up to this point, and to move through this whole curve or track, this particular train must be attached with additional engine power, additional, you can say, engine, either at the back side or either in front side. Okay, if you add extra engine in the front, it will be like used as a puller. Okay, and if you are adding a new locomotive power engine in the back side or at the last point, it will be used as a pusher. Okay, this particular uh, engine, additional engine help will help this particular train to move in this particular gradient. Okay, so in this particular gradient, this particular gradient, again I will show you a diagram. Suppose this is horizontal. Okay, this is your minimum gradient or gradient given in the station yard. this is your ruling gradient. Suppose this is your ruling gradient, and sorry, this is your uh, momentum gradient. Fine. Now this pusher gradient again higher than this momentum gradient. Okay, so this gradient, it is your pusher gradient. Okay, so pusher gradient, in the particular pusher gradient, we need an additional locomotive to attach with the train to push. Okay, so provision of ruling gradient if the provision of ruling gradient is costly, okay, so at that point along the high gradient, an extra locomotive can be used to negotiate the gradient of higher value. That means an extra locomotive can be used in terms of to use as a pusher or helper. Okay, so from this point say we can say this pusher gradient is higher than uh, momentum momentum gradient. Okay, MOG, momentum gradient, which is greater than ruling gradient, and which is greater than what? Last one is your minimum gradient. Okay, this is very important, so you should understand this thing. Okay, okay, pusher gradient is higher than momentum gradient, which is greater than your ruling gradient, and the last one, what is the minimum one? The minimum gradient, or you can say the gradient provided in the station yard. Clear up to this point? Is it clear? Yes or no? If you have any doubt till now, you can ask me, including the
Yes,
last class
sir.
also. No doubt? Okay. So now we are going to discuss about grade compensation. Okay. We're going to discuss about grade compensation. So what is actually grade compensation? Compensation means what? Reduction. Grade compensation means what? To reduce something. Okay. Or to compensate means to compensate something. Okay. Yeah. So when we need to go for grade compensation, first of all, what is grade compensation? So basically, the grade compensation is come in picture when a gradient is to give in a curve. Okay, that means suppose that there is a hill. Suppose this is a hill. This is a hill. Okay. Now a particular train need to move from this point to this point, or need to travel. Yeah, from this point to this point. Now to negotiate this part, we need to give gradient. Okay. So I think you also seen that the particular, either it is a highway or railway track, it is not provided like this. It is provided like what? It is provided like this. I think you noticing, right? So even in the hilly area, the, whether it is highway or railway, the path is little bit a kind of a curvature, curvilinear. Okay, so you can see this part is actually moving upward. Okay, this curve. Okay, again I'll show you again a new one. Wait. Suppose this is a hill, okay, and particular track. I'll show you now. Track may be like this. Okay, so it will be made like this. Okay, so for now, just try to for understanding, I have drawn this. So this is a hill. To travel from lower point to upper point, it required gradient. Okay, but also in a particular hilly area, it is not giving in a straight direction directly. It will give in a circular path. Okay, so from this point, from this point to this point, here you can see if I draw any horizontal line, you can see there is a gradient. It is not horizontal, it is going upward direction. Fine. So till now, a certain amount of gradient is provided to climb the hill. Okay, even from this point to this point, this much of gradient is provided. Okay, fine. Up to this point, it's fine. Now, when it comes to the curve, ah, sorry. Wait. Okay, okay, fine. It will come closer. Yeah. So when a particular gradient come near to the curve, basically at a particular this portion, I'm talking about this portion, this part. When a particular gradient arrive at curve, at this curve point, we don't give the particular pre-decided gradient in case of curve, because we are not discussing in about curve till now. We're coming in next class. Okay, anyway, but in highway engineering, you already know the curve. Okay, so in curve, when a particular train moves along the curve, you also know a particular centrifugal force act in outward direction. Okay, and there is a other resistance force also act nearby the curve. Okay, so to minimize the resistance, we need to go for reducing the gradient. Okay, so that means to for giving more safety or safe movement of a train over a curve, we have a two option. First option, increase the increase your radius of the curve. Okay, that means this particular curve, which is actually circular. Okay, up to this point, if I draw, forget about this, up to this point, just for imagine this part is a circular. Okay, so one option for to provide a safe movement of the train is what? Increase the radius. If you increase the radius, the curvature will be uh, broader. Okay, but this thing is not easy to provide. It contain cost, it contain time. Okay, another one, another option for safe to provide safe movement of train over the curve is to go for reduce the gradient. Okay, the amount of gradient provided here, we should minimize the gradient, especially in case of curve. Okay, at that particular reducing the gradient is called grade compensation. Okay, basically this is your grade compensation. So that means when a particular horizontal curve, when a horizontal curve meets a gradient, the gradient value has to be compensated. Okay, and this phenomena is known as grade compensation. Okay, so listen carefully. When a horizontal curve, this is a horizontal curve, all this horizontal curve, right? So when a horizontal curve meets a gradient, and gradient is what? Gradient is a longitudinal curve, right? Okay, longitudinal slope. Fine. So when a horizontal curve meets a gradient, the gradient value has to be compensated. And this phenomenon is known as grade compensation. And generally, the grade compensation can be executed by two ways. First one, grade compensation can be done by two ways. One is your increase the radius. That means that this particular curve, you can also increase the radius, but it is, I have already mentioned, it is time consuming and also expensive. Okay, it required larger area then. Okay, sometimes it is not possible. And another option is to reduce a reduction in the gradient. Fine. So it's better option. Better option is what? Go for reducing the gradient in curve, horizontal curve. Okay. And this reduction in gradient, this gradient reduction is actually depend or directly proportional to the resistance occur in the curve. That means how much gradient should be minimized is depend on how much resistance should be reduced. Okay, so we have to first calculate the amount of resisting force coming on the curve, or to encounter the resistance, that amount of gradient must be reduced. Okay, so we can write down that grade grade compensation is directly proportional, you can say, the resistance in curve. Okay, and this resistance in curve is actually inversely proportional to the radius of the curve. That means if larger radius will be there, more straight curve will come, and more straight curve, resistance will be less. Okay, so jitna radius of the curve will be large, the resistance will be less. In other word, we can say jitna radius kam hoga, utna hi कर्व स्टीप होगा और रेजिस्टेंस उतना ही ज्यादा होगा, और जितना ही रेजिस्टेंस ज्यादा होगा उसका ही उतना ही ग्रेड कंपनसेशन उतना ही होगा. दैट मीन्स द ग्रेड कंपनसेशन डिपेंड्स ऑन द रेजिस्टेंस इन कर्व and which is inversely proportional to the radius of the curve. Okay, and this particular thing directly proportional to the degree of the curve. That means this degree. Okay, the radius of the curve and degree of the curve is inversely proportional. Even in the coming classes, next class, we're going to discuss about curve, horizontal curve in railway. So in that particular class also, we're going to prove this. The radius of the curve is inversely proportional to the degree of the curve. So from this, it's very important relationship of grade compensation with resistance of the curve, okay, and the radius of the curve and degree of the curve. From this point of view, we can connect these two terms. So the grade compensation is directly proportional to the degree of the curve. Okay, so grade compensation is directly proportional to the degree of the curve. Fine. Is it clear to you? I'll show you one thing. You can see here. So what is basically grade compensation? So if a curve is provided on a track with ruling gradient, or any gradient you can say, the resistance of the track will be increased on this curve. Fine. So in order to avoid resistance beyond the allowable limit, the gradients are reduced on curve, and this reduction in gradient is known as grade compensation for curve. Okay, I already mentioned you that there is a relation between grade compensation with degree of the curve. Okay, how it related? So in India, the compensation of the curvature or grade compensation is given by this formula, or not formula actually, by this amount. So in depending on a different gauge like broad gauge, meter gauge, or narrow gauge, so what is the percentage of grade compensation? For broad gauge, it is 0.04 percentage per degree of curve. Okay, that means it is related to like that. You can also write like this. For broad gauge, the grade compensation is, you can also write like this, 0.4 d percent. You can also write like this. So grade compensation GC equal to 0.04 0.04 d percentage for broad gauge. For meter gauge, 0.03 d percentage. For narrow gauge, 0.02 d percentage. So these things are Indian standard, okay, as per Indian Road Congress. Okay, so the formula we already mentioned. This formula you have to understand, or you can say remember that grade compensation is directly proportional to the resistance in curve, which is inversely proportional to the radius of the curve, and which is directly proportional to the degree of the curve. Fine. So this is all about your grade compensation. Fine. So you can also go through this particular problem. I will show you now. Let me go. Wait. Lastly, to make you understand better, so here you can see one numerical is also there. Okay, that means in this particular numerical, you need to find out what is the uh, allowable ruling gradient after grade compensating. Okay, in curve. So there is a curve. So if ruling gradient is 1 in 250, so this is a ruling gradient. It is provided in a particular curve or in particular railway track. Okay, it is what is the ruling gradient is provided 1 in 250. Fine, on a particular section of broad gauge. Suppose it is a broad gauge railway track. Okay, and at the same time there is a curve which is of a degree of 4 degree. Okay, and a particular curve have a 4-degree curve. Okay, and it is situated in ruling gradient. Now what should be the allowable ruling gradient in curve? So generally the ruling gradient is provided is 1 in 250. Okay, but this particular amount of gradient we cannot provide in curve. We need to go for minimizing that particular gradient. How can you minimize? So for that, what information we are getting? So the gauge of the track is broad gauge, and for broad gauge, you know what is the standard amount of grade compensation is 0.04 percentage per degree of the curve. You know these things, okay? And what is that degree of the curve is provided 4 degree. Okay, so as per Indian Railway recommendation, the grade compensation for broad gauge track is, is standard. How much? 0.04 percentage per degree. Okay, now since the curve having 4 degree, we have to multiply by 4 with the 0.04. So total percentage is 0.16 percentage. It is the amount of grade compensation for this particular curve having 4 degree. Okay, now, what is the ruling gradient provided in a particular track? It is 1 in 250. So we can write 1 by 250. If you convert in percentage, multiply by 100, we will get 0.4 percentage. So this is the amount of ruling gradient provided. Okay, this is the amount of ruling gradient provided here. So this is the amount of ruling gradient provided here, and this is the total amount of grade compensation. So what is the allowable ruling gradient? Just subtract this part from this. Okay, just go for minus this. So required ruling gradient in curve, how much? 0.4 minus 0.16, that is 0.24 percentage, or in terms of 1 in n, we can write 1 in 417. This is the amount of allowable ruling gradient provided in curve after giving grade compensation. It's very easy to understand, I guess. So this is all about today class. With this, we have completed this gradient part. Next class, we start horizontal curve. Then we'll discuss about super elevation. Then we'll again go for some numerical on super elevation. Then with this, we can conclude the third module. Is it clear till now? Any doubt? Doubt hai kya? I can't hear you. I can't hear you. Your voice is very low. You can also write or just speak up. Try to go to the good network area. I can't hear you. Anything? 1 in 417 means it is just a representation of gradient, right? So basically, how gradient is represented in the previous class, I already mentioned you, right? Again, I have to go to the screen, like, wait. So basically, what is uh, how a gradient is represented? Gradient is given in terms of slope, right? So it is represented in terms of what? 1 in n. I already told you, na? It is represented in 1 in n. So you can remember this for n numbers of run. This is your n for horizontal run. 1 unit is given. So what is the slope? This is a gradient. This is the gradient, and it is represented in 1 in n, 1 vertical for n horizontal. So here you can see in this particular result is found in 1 in 417, right? That means 4, and in this case n is actually 1, sorry, 417, and here 1. For each 417 of horizontal run, we provide 1. This is a representation of gradient, right? If you convert this 0.24 percentage in this form, you will find out 0.24 divided by 100, you will get this thing, or you can say 1 divided by 417, you will get these things. Okay, so this is the representation of gradient only. Okay, anything else? Clear है? Sir. Okay, agar any doubt? Anyway, so I'll just stop my recording here. After that, I'll just take your attendance. If you have any doubt now, you can ask me. If you don't have now, after revision, if you go through any confusion, you can also get back to me. Okay, so I'm stopping my recording here.